Let's get started. So good morning, everyone. This is a very good day for learning, right? Just, just a little bit cloudy, so you can study hard, right? So, this is the second class of this course. And then, what did you learn? What did you learn from the previous class? So, in the previous class, so I briefly introduced about the digital logic design and then actually the digital systems. So I mentioned that our real world. So we live in the real world, not the fantasy world or some virtual world. So in real world, every signal is analog signal. So what is an analog signal? What is an analog signal? So analog signal means that the signal value continuously changes by time, right? So this is the analog signal. So you can think that analog signal is the continuous signal, okay? Then what is a digital signal? So digital signal, the concept of the digital signal is somewhat opposite of the analog signal. So it means the signal value is discrete. So discrete means that it's not continuous, right? So digital signal has only two values, 0 and 1, right? So it's very easy. So, and then, so as I mentioned, the most of electric devices. So currently we use many kinds of electric devices, right? So actually, these devices are very popular. And then actually, also these devices are digital systems. So it means that digital systems handle digital signals. And then, actually, so I showed the many electric devices. But what is the common part of these devices? So actually, these devices are actually computer systems. And then computer systems means that these devices include processors, okay? And then processors are, so like the CPU or GPU, so those are examples of processors. And then actually these processors are also digital systems, okay? Digital devices. So it means CPUs or GPUs handle digital signals, right? So that's why we are learning digital logic design. Okay, so this is the basic part of the digital hardware design, right? So that's what I explained in the previous class. Okay, and then I also showed these photos. Okay, so this is the first semiconductor device. It's called transistor. Okay, so it is called an integrated circuit. Okay, so what is circuit? If we build a circuit, the electric circuit, then the voltage source drives the circuit component. Also, the current flows through the circuit, right? It's like this. So okay. So this is the voltage source, and then the voltage source is connected to some components such as resistance. Okay, it's R, and then actually the electric current through the wire, it's a metal wire. So this is the circuit. Why is it called a circuit? As you can see, this circuit has a circular form, right? So it's the VDD. So it's some high voltage level. The VDD node, the high voltage node of the voltage source is connected to some components like resistance, and then it's also connected to the another node, and then it creates some circular connection, circular wires. So that's why this is called a circuit. As you can see, the circuit is the letters in the circuit is very similar to the circle, right? Circle. So very similar to the circle. Okay. It is because the wires are connected from the VDD, high voltage, to the low voltage. So actually, the most electric, we can build most of electric devices like this. Okay, so and actually, all electric devices can be built like this circuit. So it is because we need to use the electric current. Okay, to in order to learn the electric devices. So this is the first, it's the photo of the first integrated circuit. So called a transistor. So actually, the first circuit is very simple, obviously, right? Actually, the first product is actually very simple, right? And then also, actually, this circuit includes very small number of transistors. Okay, transistors is the basic component used for building logic gate. Okay, so this circuit only includes this circuit only includes the one transistor, but as you can see, the size is very large, right? And then also this is the first monolithic silicon IC. So currently we use a semiconductor technology to build electric devices, right? What is semiconductor technology? We can use silicon. Okay, semiconductor means that. So this is semiconductor. So actually, the conductor represents that the electric current can flow via a conductor. So in Korean, it is called 도체, right? 도체, right? But semi means that it's kind of a half. So it means that it's a half conductor, right? Half conductor means that we can control the electric current flows via these semiconductor devices. So we will learn about the semiconductor devices later. So actually we use these semiconductor devices to build these systems, right? Then actually you can see that this big photo, and then also this photo also includes the very small number, actually two. Okay, this photo shows the two semiconductor devices, that's two transistors actually. Okay, so it was very simple in the maybe 30 years ago. So now, and then this is the photo of the early ICE design. So actually, as you can see, the system was getting more complex. So it means that this electric device system includes more transistors. So it means that we can build more complex and then better, okay, better these systems using more transistors, right? But as you can see, so in the previous time, we cannot use the computers for designing these IC devices. So we just drew a circuit like this, okay? And then like this. So many engineers actually. So this actually this diagram is called a schematic. schematic of the transistor, and then actually the early time, many people drew the schematic on the paper like this. So it is because the system was very simple, okay, and then a system includes a few number of transistors. Okay, so it's the early digitized design. So as you can see, you can see the name of Intel here. So Intel is the most famous IC semiconductor company, the most famous CPU vendor. Okay, so but you can find that it is more complex, right? It's more complex than the this figure, this schematic, but so it's okay. So actually, we can see some wire connection, and then we can see some components, and then also we can see some transistors in this photo. So this, as I mentioned, this is the first processor made by Intel. It's launched in 1974, and then the clock frequency is very low. Okay, so currently, so what is the clock frequency of your smartphone CPU? What is the clock frequency of your smartphone CPU? No one knows. But everyone wants. So no one is interested in your smartphone CPU or smartphone specification. But everyone wants to use better smartphone, right? So why I mentioned clock frequency here? Because the clock frequency is tightly clock frequency is tightly connected to the performance. So it means that usually, so I mentioned usually if a processor runs with higher clock frequency, it means that the performance of this processor, it can be higher. Okay, so it means that if we use a higher clock frequency, then we can you can use a better processor. So it means if your smartphone CPU runs with higher clock frequency, then you can say that, oh, my smartphone is better than yours. It's not always true, but usually, okay. But as you can see, clock frequency. The clock frequency of the early CPU is 2 megahertz, and then recently, the Intel desktop CPU, the clock frequency can be up to 5 gigahertz. Okay, it's a giga. So giga is the 1,000 mega. Okay, so it means that actually we can say that this CPU is much slower than the current CPU. It is because the clock frequency is just megahertz scale. Okay, and then what is the technology now? So actually, you need to focus. You need to focus on some semiconductor technology. So actually, so as I mentioned in the previous class, semiconductor technology is very, very important for some industry, and then also, so actually this is actually for a computer industry, like this semiconductor technology is very, very critical. Okay, so also I mentioned in the previous class, but recently every nation focuses on developing their own semiconductor fab. It's a factory. Okay, so it is because this technology is very important, very critical. Okay, so if you are interested in those some semiconductor technologies, and then if you are interested in some stocks of NVIDIA, some TSMC or Intel, like the semiconductor vendors, or Samsung or Hynix, then you can, I believe you can have heard about some technology node, like the 5 nanometer was 3 nanometer. It represents some technology node of the semiconductor technology. And if this value is smaller, so it means that we can use better semiconductor technology. So recently, TSMC used the 3 nanometer or 5 nanometer technology. It's very small number, so it means that this technology is it's a high technology. But in 1974, the technology node was 6 micrometer, and then as you can see, this is the 6,000 nanometer. So currently we are using 3 nanometer or 5 nanometer technology. So compared to this value, you can find that this number is much larger than the current number. So 3 nanometer or 5 nanometer, right? And the number of transistor is 4,500. Okay, and then you can compare it to some modern chips. So it's not modern because this is the Haswell architecture. So recently, we can use the kind of I forgot the name, Elder Lake or some other lake Intel architecture, right? So Elder Lake is the kind of previous year. I forgot the code name of the Intel CPU, but so currently we can use some Elder Lake or some other lake Intel architecture. But Haswell is the kind of some old generation of Intel CPU. But as you can see, so the technology now is a 22 nanometer, and then the number of transistors is billions of transistors. Okay, and then there are 18 cores. Okay, so it means that this chip includes you can say that this chip includes 18 CPUs. Okay, but you can compare this value, the number of transistors. So compared to the early processor, this processor only includes thousands of transistors, but current digital chips includes around the billions of transistors. So how can we design this processor? We can use this processor, right? So we can also use some smartphone processors such as the Qualcomm Snapdragon. We can also frequently use the processors such as Exynos, by Samsung. So also we frequently use GPUs for game applications or machine learning applications, right? And then actually these chips includes, so these chips includes the billions of transistors. So how can we design? So if this number is higher, so it means that this system is very, very complex, right? So we can something like this. So we need, so firstly, this is the very early the schematic of the very old circuit. But as you can see, you can find some transistors here, and then by drawing some transistors, then we can design a chip. But in this figure, that we can find how many transistors? Maybe 4 to 6 transistors in this figure, right? The human, an engineer designed this circuit, right? And then the modern chip. A modern chip includes billions of transistors. How can you design? Oh, it's not possible. So someone says that the Intel has Alien, so Alien can design their CPUs, but it's not true. So human designed the Intel CPU. So actually, so we can say that IC design, actually the system design is actually very complex job. Okay, then so it means that in order to build a single computer systems, and then a single computer systems include many chips. So CPUs, also the board chips, also memories, and then also other I/O chips. Okay, actually a CPU, a computer systems include many different chips, and then by assembling these many chips, that we can build a single computer system, right? So it means I mentioned that in the previous class. We need to learn. We need to know about the computer system as a computer engineering student, right? But how? I mentioned, this system is very, very complex. And then actually, this system includes the billions of transistors. Then how can we understand? How can we learn in during 4 years of this university time, maybe? So I will explain in this time. And so also I will show that this some other trend of the IC design, the transistor, the semiconductor industry. So have you heard about the Moore's law? Anyone? What is Moore's law? So Moore's law, actually this is very popular law in the semiconductor industry. Why? We can expect the number of transistors. So we can expect the complexity of a single chip can be more complex by time based on the Moore's law. So actually Moore's law says that the number of transistors, in a chip, my writing is not good. The number of transistors in a chip will double, multiplied by 2 every 2 years. So it explains the trend of semiconductor technology. Okay, so and then also we can say that our chip, our processor, the complexity of our processor increases by 2 every 2 years. So it means the system gets more complex by time. Okay, so it means a single chip includes more transistors. So you can say, that's fine. What is fine? So it means it's double every 2 years. So it means that the number of transistors increases exponentially, not linearly. Okay, so the complexity increases exponentially. Okay, so Moore's law says that the number of transistors, the integration of the transistor becomes increases exponentially by years. Okay, so and then it's true actually. So this graph shows the number of transistors in a CPU, and then you can this x-axis represent the year. Okay, so and then as you can see, this is the y-axis represent the number of transistors, but you can find that the y-axis is the log scale. Okay, and then you can find that, oh, by years, the number of transistors per chip increases linearly in this graph, but it means I mentioned that y-axis is the log scale, so actually exponentially. Okay, actually in a linear graph, it looks like this. It's true. Okay, so system gets more complex. So how can we design? How can we understand? How can you understand that these are complex systems? So these complex computer systems. But we can start from the very simple simple base, very simple algebra, or very simple discipline. So what does that mean? Firstly, I introduced about the digital signals, right? And then I mentioned that we are living in the real world, and then every signal in our real world is analog signals. So analog signal means that so signal changes continuously. So which means that this signal can have many possible values, right? As I mentioned, this like 0.001, 0.002, 0.1111, like this. But then why do we use digital signal even though we live in the analog world? Because it's simple. So we convert complex signals or complex data into simple digital signal or simple digital data. So in order to build system more, in order to build system simpler, okay? So we can just handle the 0 and 1. But even though we use build the system, but we can also know that our digital system includes many transistors, like billions of transistors. Now how can we design? So actually, one person cannot design this entire entire system. So many engineers are required for designing this very complex chip. But how? How can we manage it? So in order to build a single chip, then we need to manage these complex systems. But then how? Okay. How? So I will explain about the art of managing complexity in digital systems. Okay. Okay. As I mentioned, this is too complex, and then this is too big to fit in our brain. So, but we can use these approaches or these concepts. So as you can see, you can find the abstraction and discipline, and then the theory-wise here, the hierarchy, modularity, and regularity. So these are some principles for designing very complex systems. Okay. Okay. We will in the today's class, I will briefly explain about these terms. Okay, abstraction and discipline, and then hierarchy, modularity, and regularity. So based on the these principles, we can design very complex systems, and then this is the very common approach for understanding complex systems. Okay, actually, the abstraction is a very important concept in computer engineering field or computer science field. Okay, so let's learn about the abstraction. So what can you see in this slide? So you can see a very cute girl, okay, and then she's driving. oh, it's illegal, right? But she's driving. So think about some system in real world. So a car. So can you understand how the car works? So it means that can you understand the car system entirely? No, but why? So actually a car is a very complex system, but we can use a car, right? So you are a student, so but I believe some of you already have a driver license, like driver licenses, but it means that you can drive a car. So I have a driver license. That how? Even though, sorry, even though a target system, car is a target system for use, but even though a target system is very, very complex, and then we cannot understand this target system, right? But we can drive a car. How? We don't need to. So we don't need to. We don't need to know. We don't need to know about the detailed mechanism or detailed components inside of a car to drive a car. Right? In order to get a driving license, we can learn how to use handle and how to use acceleration pedal, and then how to use a brake, right? And that's it. So I want to say that even though the target system is very, very complex, but only the simpler things, only the required knowledge, only the required knowledge is revealed to the driver. Okay? So this is a concept of abstraction. So even though a target system is very, very complex, we don't need to understand the entire mechanism or entire organization of the target system. In order to use this target system, or in order to understand this target system, we can understand the only a few required things. So we only a part of required knowledge. So even this is the machine details of a car. So a car includes mechanical engines. Also, a car has some very complex braking system, something like that. Also, a car also includes the very complex electric systems, right? But we don't need to understand. Only the required knowledge, like the handle, and then some pedals, and then some these buttons are revealed to users. Okay, so this is a concept of abstraction. So, and then this is another example. So this is a vending machine. So we can use a vending machine, but we don't need to understand how the vending machine works. Okay, because we are just user, and then actually in order to use a vending machine, then only some required interface. So this is the interface. So we don't know the inside of a vending machine, right? We don't know about the inside mechanism, the inside the processors of a vending machine, but only the required interface. So this is some some boundary between the inside of a vending machine and then the outside of a vending machine. This is an interface. So like the buttons and then some how can I say, it's a coin slab of money. Yeah. So these are just revealed to users. Okay. Some interfaces are just revealed to users, but inside is hidden. So this is a concept of abstraction. Okay. So what is abstraction? Abstraction means hiding details when they aren't important. So if some details are not required for using, or some details are not required for understanding, then these details can be hidden. So this is a concept of abstraction. So providing only required interface. Okay. So interface, as I mentioned, the interface is the revealed part from the some inner part. So revealed to the outer part, but only the required interface is revealed to the some outer part. So why did I explain abstraction? So it is because we can also apply the same approach to understand the complex system like a computer system. Okay, so as you can see, so this figure shows the some layers of inside of a computer system. So as you can see, a computer, in order to understand the computer system, actually we can start from the some basic physics knowledge of physics. So actually we need to understand how the electrons move inside of a circuit. So it means that actually not to build a computer system. So this is an electric device, but in order to build an electric device, then we need to understand the electric physics, right? So how the electrons move inside of a circuit like this? And then another level is the device level. So based on some basic knowledge of electric physics, and then we can build the very simple devices. So as I mentioned, we recently used the semiconductor technology. So using this electric physics knowledge, then we can build semiconductor devices like MOS transistors. So CMOS transistors, MOS or PMOS transistors. And then using transistors, we can build analog circuits, and then we can build some digital circuits and logic and architecture like this. Also, I showed this figure in the previous class, and then I mentioned that this usually in the electrical engineering. So electrical engineering covers this area, and then computer engineering covers these areas. Okay, but I want to show the many layers. So in order to understand a computer system, actually, as I mentioned, a computer system is a very complex system. So actually, we cannot understand every aspect of these layers. Actually, in order to build a single computer system, the knowledge of all layers are required, but we can just focus on a certain layer of a computer system. So this is because this part is very complex, and then it's very, very difficult. Okay. So we just focus on a certain layers of a computer system. And then in this course, we will just focus on the circuit. As you can see, you can find the AND gate, NOT gate here. So these are basic logic gates. And then also we will focus on logic, okay, like the adders and memories. And then as you can see, so these layers, like architecture or microarchitecture layers, will be covered by computer architecture course, the COSE222, okay? And then some other courses will cover this higher upper layers, okay? But we can just focus on a certain layer. Then on the other layers, such as the analog circuit and devices, physics, these parts are just hidden, okay? We don't need to understand. But we need to understand some is boundary knowledge it is a interface, right? So in order to use the lower layer of a computer system, then we need to understand the interface between layers, okay? So this is the abstraction. So abstraction is a very important concept in the computer engineering. So actually, we just focus on the required knowledge. Okay. It's the same for software. Actually, the software engineers do not understand about the hardware. Actually, so they just focus on programming, and then they just try to understand some interface from the hardware, so some signals from hardware, and that's it. But in order to build so this is the advantage of abstraction. So it means that we don't need to study, we don't need to know about some details of a complex system. Then we just focus on a certain layer of a system. But this approach also has a disadvantage. So what is the disadvantage of this approach, like abstraction? Global optimization. So global optimization is very difficult. It's very difficult to get optimized result. So globally optimized result. So it is because we just focus on a certain layer like microarchitecture. So for example, we can just develop a better CPU by enhancing microarchitecture of a CPU. But in order to build a better CPU, some other knowledges such as the logic part, digital circuit part, and then some these parts are also required. But we can just focus on this part. So global optimization. If we just use the abstraction, this approach like abstraction, the global optimization is not. So usually it's not possible. Okay, we just get some local optimization result. Okay, so sometimes, I just showed some layers of this computer system, but you can find that the software part has also very complex layers. Okay, and then because such a system includes many layers, this system is not optimized. So sometimes if a certain layer is integrated, then we can improve the performance dramatically. So it is because a certain system is divided and we cannot get globally optimized performance or globally optimized cost. Okay, so this is a disadvantage of abstraction. Okay, so I just showed some example of an abstraction. So what can you see? Now this is a photo, diphoto of Intel CPU. So what can we get? What can we get from this Intel CPU diphoto? So what can you understand? What can you understand from this figure, this photo? So you can find that this photo is very beautiful. So many, there are many transistors here, and that's it. I don't know. But so actually I added some rectangles above the photo, and then actually I just added some names of a component under this diphoto. But we cannot understand the detailed logic or detailed component inside of this component. But by adding some blocks like system agent, a CPU core here, and GPU core, then we can understand more about the Intel CPU, right? So if we just see this photo, we can understand, this Intel CPU includes 4 CPU cores, right? So this is this Intel CPU includes the multi-core architecture because there are 4 cores. Also, this Intel CPU can include the GPU, so which means that we don't need to buy another GPU card for building a computer system because the CPU already includes the GPU. Okay, and then memory controller is here, so we can expect that DRAM can be connected via this part. So actually, every component is not revealed. Every knowledge is not revealed by this abstraction, but by applying some different level of abstraction, then we can understand more. We can understand more about this Intel CPU. So we can get a certain knowledge about the Intel CPU by this abstraction level. Okay. Yeah, this is some concept of abstraction. So only the required knowledge is revealed. Okay. So if we just use the different level of abstraction, then the content of knowledge is also different. Okay. Okay, discipline. So discipline is a kind of so in Korean is kind of 훈육 or some 교육, but it's different from the education. The discipline is just kind of some 규율, or so it's a kind of some restrictions, right? So as you can see, the definition of discipline is intentionally restrict design choices. Okay, so we can say that a discipline is related to the restrictions because it restricts our behavior. So it's the same for the design. Okay, so intentionally restrict design choices. So example is the digital discipline. So I mentioned that analog signals can have many possible values, but this analog signal can be understood like this. But what is different? The shape is different, but from this analog signal, we can just say that, this part is 1, and then this low part is 0. So 1, 0, 1, 0. So we can understand like this using a digital signal, but actual signals looks like this. Actual signal looks like this, like continuous waveform. But we just understand, oh, this part is 1, this part is 0, 1, 0, 1, 0, because this is low value. So this simply means that we restrict some values, we restrict some design choices of the target signal. This is the discipline. So why? We want simplify. We want to simplify a target system. That's why we apply discipline approach for the data system. Okay. And then there are three Y's: hierarchy, modularity, and then regularity. So these are also some basic approach for building complex systems. So you can see the definition of these three Y's. Okay? Hierarchy means that a system divided into modules and sub-modules. What does that mean? So what is hierarchy? So in Korean, it means 계층 구조, right? But actually, hierarchy means that it's kind of some level of social status, social status or social level, right? So different level. But in computer design or in digital design, the hierarchy means that it's a kind of a large module. A large module includes the many sub-modules like this. So it means these sub-modules are included in this large module. Okay, so we can find some hierarchy here. And then this is called the hierarchical design. Okay, so and then this complex system can be divided into more simpler small sub-modules. Then we can just build the system more easily, right? This is the hierarchy. And what is modularity? The modularity means that the well-defined functions and interface. So actually, in this course, so we will learn about modules. So actually, I will frequently show a black box. Okay, black box here. But this is a module. Okay, it's a module. A module of a system, and then a module is defined. Then we need to define some interfaces like input and output ports. Okay, input and output interfaces, and then also functional modules. Okay, so modularity means that a component. A module has some well-defined functions or interfaces. Okay, this is called modularity. And then regularity. You can find that the regularity means that, so it's regular. So regular means that we can use the same component. Okay, and then we can use the same component repeatedly, like copy and paste. So when you design a certain, when you build a PowerPoint slide, you can just repeat the same figure, and we can copy and paste the same figures, same rectangles, right? Shapes. So it's the same to the design. So regularity means that, even though our system is very large, our system includes the same components. And then these same components are So many same components are implemented inside of a complex system. This is regularity. So I will show the example. The first example is hierarchy. So, okay, you can find it here. So this is another diagram of Intel CPU. So this is the Intel Skylake CPU topology. So this is architecture of server CPU, and then server CPU includes actually many cores. So like you can find the core here, right? You can find many cores here. Okay, like those 20 cores inside of a single chip. But inside of each core, you can find the different many components like here. Okay. So this is an example of hierarchical design, right? So this is a single chip, right? Inside of a single chip, there are many sub-modules, many smaller components, like many cores, many interface, like PCIe, and then some DRAM controllers here. So we can find many sub-modules inside of an entire chip. And then if we just focus on a single core, this single core also includes the many components. So this is hierarchical design. Okay. So large module includes many smaller sub-modules. So we can design this complex system like this. Okay. How? We can just focus on the smaller sub-modules. Okay. We can design a smaller sub-modules, and then by connecting these smaller modules, some smaller sub-modules, then we can build large module. Okay, this is a hierarchical design, and then based on this hierarchical design, then we can build a large system. Modularity. So this is an example of modularity, and then as I mentioned, when we design a module, then we need to define interface like input and output port of a module and function. So this is an example of a register file. So you will learn about the register file in the computer architecture course. Okay, but you can find the function of register file and the interface of a register file here. What is the function? Function is read register data indexed by read register number. So the function of a module is defined, and then so another function is the write register data indexed by write register number if read write equal 1. So this is the defined function of a register file. Okay, we define a function of this module. So this is a module, and then also in this module you can find some interface. So it means some input ports here. These are input ports, right and write data, and then you can find the output port here. So when a module is designed, function should be defined also input and output. Input and output interfaces needs to be defined. Okay, why? Just the interface is defined. So let us assume that you are designing this register file, and then this register file will be connected to the other module, like module A and then module B. Is your register file. But this module A and module B will be designed by other people, other students, right? Then how can we connect? How can we connect these modules to build larger module. It's a hierarchical design. Actually, the student who are designing this module A does not need to understand the detailed operation of register file, right? Because he or she is focusing on designing this module, but he or she designing this module A needs to understand this part, because signals from this module A is connected to the register file. So he or she needs to understand the interface between register file. Okay, so modularity. Modularity means that we actually the inside of a module is hidden, but required information like the functions and then interface. So information about the functions of a module or functions of an interface needs to be defined, needs to be revealed. Okay. For what? Not to design larger module. So hierarchically. Regularity. So what is regularity? Now, I said that the regularity is similar to copy and paste, right? The same module can be repeatedly used inside of a larger system. Well, so you can see the same topology of in the Skylake, but we can find a regularity here. Why? Because same core, same cores are included inside of a single chip. So what is the benefit of regularity? So we don't need to design different cores. Okay, we can just copy and paste. You can just copy and paste the design of this single core to build a large chip or large CPU. Okay, so that's why we can build very complex processors that includes billions of transistors. Okay, even though Intel CPU includes the billions of transistors, we can just copy and paste the same cores, and then we can just include these same cores, many same cores inside of a single chip. Then we can build a large chip. Okay, we don't need to design different cores. It's the same for the GPU. GPU also includes the billions of transistors. You know, the recently the GPU is the NVIDIA GPU is kind of one of the largest chip. Okay, but GPU also includes the many same cores. Okay, we don't need to design the different cores inside of a GPU or CPU. We can just copy and paste. Why? Because of regularity. Okay, if we just use the regular design, then we can just repeatedly use the same design. Okay. Okay. So these are some approaches for designing the complex system. Okay. So I just mentioned that the modern chip, the modern processors are very complex system, but you don't need to worry because we can apply these approaches like abstraction, discipline, and hierarchy, modularity, and regularity. Thereby using these approaches, then we can build very complex systems. Okay. So you need to understand a complex system like this. Actually, in the real world, it's also same for the real world. If you want to understand some complex systems like the social systems and some other systems, you can apply the same similar approaches. Okay, abstraction, discipline, and then 3 Ys, hierarchy, modularity, and regularity. Okay, that's how we can design a complex system. Okay, then so until here, I just explained about some approaches, the required approaches for designing a complex system. Now, so I will explain about the digital abstraction. So we have 10 minutes till the end of the class. Okay. So also you can find another abstraction here, but it is called digital abstraction. Okay. So what is a digital abstraction? So what is abstraction? What is the meaning of an abstraction? So abstraction means that some difficult part. The difficult parts are hidden. Okay, we can only understand those some required analysis. Okay, so this is abstraction. Then what is digital abstraction? So okay, so we have only 2 slides. Okay, digital abstraction means that, so I mentioned that in the real world, every signal is analog signal, right? And then also I mentioned that we use digital devices, like most of electric devices are actually digital systems, okay, digital devices. So it means that these devices handle digital signals. But we use our devices in the real world actually, right? We use our smartphone in the real world. We just see the display like this in the real world. Right. Actually, we use how can I say? So we use our smartwatch. We can see the smartwatch in the real world. Right. How? I said that actually the digital devices just handle digital signals, and the digital signals just have 1 and 0, but real analog signals actually are continuous. And then also another part is that these are electric devices. So which means that we need to build electric circuits using voltage devices like a voltage source, and then current level, and then RLC, these the resistance, inductance, and capacitance. So these are required components for building electric circuits. So actually, we need to build analog electric circuit, right? But this analog electric circuit can be represented to digital signals using digital abstraction. So actually, you can say, how can we understand? But actually, it's simple. So actually, the analog signal in these electric circuits can be understood like digital signals. Okay, this is digital abstraction. So let's think about this one. So you can find that most physical variables are continuous, so which means that actually in the real world, in the real hardware, every signals are analog signals actually. Okay, but we can understand we can understand these analog signals like digital signals. Okay. So for example, we use the voltage level, okay, in the real world. Then we can use some current level, electric current in these electric devices. But these values, like so, and the analog means that our CPU works with the voltage level 1.1 volt. Oh, it's my CPU, but your CPU works with the 1.2 volt. That can be possible, right? Because we are living in a real world, and actually real world actually, and the signals in real world are analog signals. Okay, it can be possible. Here, the voltage level can be different, but its abstraction means that 1.1 volt is 1. 1.2 volt is also 1. We can understand like this. Okay, so this is the digital abstraction. So voltage level. So voltage level of an electric circuit is actually analog signal. But we can understand, we can represent these analog signals like digital signals. Okay, this is the digital abstraction. So details. Analog details are just hidden. We can just understand some digital information from analog signals. So this is the fundamental some digital abstraction. So I said that digital signals have only two values, 1 and 0. And then we just use 1 for the meaning of true, right? So if a certain value is true, we can use 1. Or high. What does that mean? High. So if a value is high, then we can say that, this value is 1. That's it. 0. 0 is opposite of 1. So 0 means false or low. So we can use the 1 as the true, meaning of true, and high, 0 for the meaning of false and low. Then what does that mean, high and low? Usually, I said that, this is the electric circuit. Okay? So this is the voltage source. So actually, VDD, the higher voltage level, is connected to the component, and then is connected to the ground. It's a low voltage level. Okay, so this is the typical electric circuit. So there is, in the voltage source, there are two nodes: the high voltage node and the low voltage node. High voltage node is called the VDD, and then low voltage node is called ground. The digital level, I said that 1 means high, 0 means low. So we can understand this electric circuit like this. This is the VDD, right? So it's a high voltage. It means 1. This is ground. So ground, it means the low voltage. This is 0. Okay, we can understand the analog voltage like this. So even though the voltage level is analog signal, but we can understand like this. So if the voltage level is high, this is 1. If a voltage level is low or ground, near ground, then this is 0. Okay, so this is the digital abstraction. So it means you can understand that electric devices actually we use electric devices in the real world. Actually, the electric devices we handle analog signals, but we can understand the analog signals like digital signals, like high, it's 1, low, it's 0, like this. Okay. Okay, so I will stop here. And then, any questions? Thank you for your listening. See you in the next class. 감사합니다.